or you can do this like a power m is equal to a power m plus r, then is equal to a power m plus 2r, and now a power, again you can write it as a power m into a power 2r. A power m is again equal to a power m plus r, so it will be equal to then a power m plus 3r, and so on. Continue this. By continuing this process, so we have the following: a power m is equal to a power m plus qr for all q greater or equal. So this relation is very important for the case when there is repetition among the elements of it. Now, by this minimality of m and r, we can see that by minimality of m and r, so it can be easily verified that these elements a square, a power m, then a power m plus 1, and so on up to a power m plus r minus 1 are all distinct, are all distinct. After this element a power m plus r minus 1, we have a power m plus r, but a power m plus r is same as a power m. And since m and r are the least elements with that property, a power m is equal to a power m plus r, so there is no repetition among these elements, so they are all distinct. These elements are all distinct. And we show that this subgroup generated by a, it's equal to a square, a power m plus r minus 1. It's equal to this. The semigroup, it's a finite semigroup, finite monogenic semigroup. In that case, it has finite number of elements, m plus r minus 1. We'll see that case. So they are all distinct. That's already discussed. Now we show that any other power of a other than these powers 1, 2, m up to m plus r minus 1, any other power, a power, that element must be equal to a power some number among these numbers 1 to m plus r minus 1. So let's choose any integer. Let s be greater than m plus r minus 1. M plus r minus 1. M plus r minus 1. Then by division algorithm, there exist, we can divide this s by r, there exist by division algorithm, we divide can have so let's take this as not greater than m plus r. Let's take this as greater or equal to m, only greater or equal to m. Then by division algorithm, we can see that there is q greater or equal to 0. There is q greater or equal to 0, and this 0 less or equal to u less or equal to r minus 1, such that s is equal to m plus qr plus u. Okay, this u is actually the remainder. Actually, it's here s minus m. S minus m is greater or equal to 0. So then we can find q and u and divide s minus m by r. Actually, we divide s minus m by integer r. By division algorithm, we can find q and u, where u lies between 0 and r minus 1, such that s is equal to m plus qr plus 1. So you can also say this s is greater than m as well. Greater or equal to m is okay. So s minus m is greater or equal to 0. it's greater or equal to 0. Now we divide this s minus m by r, then we can find integers q and u with this property. Okay, so this gives a power s is equal to a power m plus qr plus u. Okay, because s is equal to m plus qr plus u, and which is equal to a power m plus qr into a power u. Okay, and a power m plus qr is equal to a power m. It is already discussed. A power m plus 1, a power m is equal to a power m plus r, which is equal to a power m plus 2r, and so on. So a power m plus qr is equal to a power m into a power u. So that's equal to a power m plus u. So any power as far as greater or equal to m, it's equal to a power m plus u, where 0 less or equal to u, less or equal to r minus 1. So any other power which is greater or equal to m, because s is greater or equal to m, either it's a power, if s is equal to m, then a power m is equal to a power m, that's clear. If s is greater than m, then a power m, if s is greater than m, then a power s is equal to a power m plus u, where 0 less or equal to u, less or equal to r minus 1. So that means any power of a which is greater or equal to m is either a power m or a power m plus 1 or a power m plus 2 and so on, a power m plus r minus 1. Any power of a which is greater or equal to m, a power s, where s is greater or equal to m, it's equal to either a power m plus 0, because u may be 0, or a power m plus 1 or a power m plus 2 and so on, a power m plus r minus 1. So thus we can say, this is equal to, first we have a square, a power m, then we have a power m plus 1 and so on, a power m plus r minus 1, because it's at most this, a power m plus u, where u is at most r minus 1. So then we have a power m plus r, which is equal to a power m. Then we have a power m plus r plus 1, that's equal to a power m plus 1. So you can see it's equal to this. So this set is equal to this. First we have proved that they are all distinct. Then we have proved that any other power is among these elements, is among the powers of these elements. So that means this monogenic semigroup is equal to this. And in this case we can say it's a finite monogenic semigroup, because it has finite number of elements. And you can see that this number of elements in that finite monogenic semigroup is equal to m plus r minus 1. M plus r minus 1. So that's equal to index of A plus r is the period of A minus 1. So order of a finite monogenic semigroup generated by A is equal to index of A plus period of A minus 1, and this order is also called the order of A, because as in case of groups, if G is a finite group generated by an element A, then order of A is same as the order of the group generated by A. So therefore we can say order of A is equal to, because order of A is same as the order of the semigroup generated by A, finite semigroup, which is equal to index of A plus period of A minus 1. So in semigroups we can define order of an element by it's equal to index of A plus period of A minus 1. So it's not like that the least positive integer n such that A power n is equal to identity, because we don't have identities here. So we define here order of an element is equal to the order of of a monogenic semigroup generated by A. So if it is finite like this, then it's equal to index of A plus period of A minus 1. In case it is infinite, then we can say order of A is infinite. In the first case, like in first case, in that case it was isomorphic to n plus. So in that case, the order of a monogenic semigroup is infinite. So that means order of an element is also infinite in that case. And in this case, it's equal to index of A plus period of A minus 1. Okay, yeah. Now, so that proves this what. So this is A power m is equal to A power m plus I. That's the first part. Now we put second part. A power u and v, they belong to A power m plus u is equal to A power m plus v if and only if u is congruent to v mod r. V mod r. Now we will prove this part first. Then we discuss. Then we discuss this. Then we discuss this one. What is it? The third part. Okay. Then we prove this C part and D part. Then this we have already proved. This C part we have proved. The monogenic semigroup generated by A is equal to A square so on up to A power m plus r minus 1. This we have proved. And we have also proved this one, A power m is equal to A power m plus r. We have proved more general. A power m is equal to A power m plus q r for every positive integer q. Now we prove the second part, B part. The B part of second case. Okay. If there is repetition. Now we first prove the second part. So let's do its second part. Second part means u v belongs to n0. A power m plus u is equal to A power m plus v if and only if u is congruent to v mod r. This part. Okay. Now suppose A power m plus u is equal to A power m plus v. Suppose, and we can say suppose u is greater than v. Okay, u is greater than v. Let's take this case. Suppose A power m plus u is equal to A power m plus v. A power m plus v. Then this implies now we check this one. A power m plus u minus 1. A power m plus u minus 1. Let's take the case u is greater than v here. It may be less or greater. So let's take this greater than without loss of generality, which is equal to A power m into A power u minus v, and which is equal to A power m plus qr into A power u minus v. For every q greater or equal to 1, and this is equal to A power m plus qr, A power m plus u. I can write here A power m plus u into A power qr minus v. So this can be done. We can choose q so large such that qr minus v is positive, because A power positive numbers on the A power positive numbers are defined. A power negative number is not defined here. So since this is true for every q greater or equal to 1, we choose q so large such that qr minus v is a positive integer, because v is a fixed integer, positive integer. Okay, so can choose q so large such that qr minus v is positive, such that qr minus v is positive. So if qr minus v is positive, then we can write it as A power m plus u plus q r minus v, which is equal to a power m plus u into a power q r minus v. So this is well defined because this number is now positive because q is chosen sufficiently large. Okay. So now this is equal to a power m plus qr, because we are given that here a power m plus u is equal to a power m plus v. So this is equal to a power m plus v into a power qr minus v. Okay, so that implies that's equal to, now v and v will go, it's equal to a power a power m plus qr, that's equal to a power m. So thus we have a power m is equal to a power m plus u minus v. But since r is the least positive integer with the property that a power m is equal to a power u minus v, so this implies r is less than u minus v, but at the same time it also divides u minus v. You can easily verify it. It's less than, then you can apply the division algorithm actually for r and u minus v, and you can see that r divides u minus v. That's very simple. As in case of groups, when we define the order of an element which is the least positive integer, that's very simple. You can easily verify it. As in case of groups, when we have a is an element of finite order, suppose order of a is equal to say n, and if a power m is also equal to e, since a power n is also e, because order of a is equal to n, but this n is the least, and a power m is equal to e, m is also positive integer, so that means m is greater or equal to n. Then we apply division algorithm, and we can see that here n divides m. This least one, it divides m. So this follows from division algorithm, and same is the case here. Since r is the least positive integer such that a power m is equal to a power m plus r, then we can easily verify that this least positive integer having this property, it divides that one, u minus v, by division algorithm. Use division algorithm. Okay, use division algorithm here. And this means u is congruent to v mod r. So this implies u is congruent to v mod r. Page 9 here. U is congruent to v mod r. So that proves one way, if a power m is plus u is equal to a power m plus v, then u is congruent to v mod r. Now we assume that u is congruent to, now assume that u is congruent to v mod r. We show that a power m plus u is equal to a power m plus v. So u is congruent to v mod r means r divides u minus v. So that means u minus v is equal to some integer into r, s into r, where s belongs to say n. So that means u is equal to v plus sr. So now we calculate a power m. Let's adding m on both sides. M plus u is equal to m plus v plus sr. So which implies a power m plus u is equal to a power m plus v plus sr. So that's called a power v into a power m plus sr. So this is equal to a power v into a power m plus sr is a power m, because a plus m plus qr. A power m plus qr is equal to a power m for every q. So in particular, a power m plus sr is equal to a power m. That's equal to a power m plus v. So this proves the part third of this second case. Part second. Part third is already proved. Now we prove the last part. That is this K. It's a cyclic subgroup. It's a cyclic subgroup of this monogenic semigroup. A.